Swayam Prabha. Digital India. Educated India.
In the previous module, if you recall, we were discussing about memory management. There we discussed broadly two techniques. One was based on contiguous memory allocation, other was based on a method called paging, where we said that the different parts or pages of a process can be loaded in different areas of main memory. But one thing was assumed: before execution starts, the entire address space of a process, the entire program has to be loaded into main memory. Okay. But in the present module, we discuss something on virtual memory, where we relax that restriction. We say that it is not necessary to load the whole process into memory at the time of execution when you start the execution process. So, we see how this can be done. Okay. So, this is the module on virtual memory. Okay. This is the first lecture. So, we start by discussing some of the basic concepts, how it works. Okay. As I said, what we discussed earlier is that when a process executes, when you run a process, the first thing that you need to do is to load the program into main memory. Why is this necessary? The main reason is that the program, the instructions of a program execute on a processor, on a CPU, and CPU can only access the main memory directly. It fetches an instruction from main memory, executes it, and then whatever is the result, it can store back into main memory. So, unless the program is loaded into main memory, the CPU cannot execute it. So, this is one of the main requirements. When we start executing a program, the instructions must be in the main memory. But if you say that I want to load the entire program into main memory before the execution starts, then a limitation naturally comes in. Depending on the size of the physical memory, the maximum size of a process gets limited. If my main memory space is 1 gigabyte, my entire process cannot be larger than 1 gigabyte. Okay? This becomes a hard restriction or limitation. And there is another thing to notice is that, suppose my program may be very large, but the entire address space, the entire range of the program, we say that the entire address space of the process, when you are running it, it is very rarely used. It is rarely used. What do you mean by rarely used? The program may be very long, but there are different parts of the programs which will be called only under exceptional conditions, when some special inputs are provided, when there are some error conditions, and so on. So, those parts of the programs are not executed or not run, let us say 99% of the time. Maybe 1% of the time when such an input or such an error condition comes, then only you need to run those parts of the program. But if you say I have to load everything into memory, whether we use it or not, it is clearly a wastage of memory, right? The parts that we are not using, not needing, we are also loading that part. So, these are the main motivations behind having something called virtual memory. Let us see the motivation. What is our motivation here? So, in virtual memory, what you say is that the entire process address space need not be in the memory at the time of execution. When you start a process, it is not required to have that hard restriction that the entire process has to be loaded in memory. No. What do? We bring only those portions of the program that are actually needed. This makes sense, right? So, when I have a program, the parts of the program that are actually needed during execution, you bring only those parts in memory. The parts which are not used, we do not bring. So, naturally there are a number of advantages. The total memory requirement of the process will be less. We can accommodate more number of processes in memory and so on. Okay? This is the main idea. We are not bringing the entire address space, we are bringing only those parts which are actually needed during execution. But where is the actual, but somehow the whole process must be stored or residing, right. So, when needed I can bring it from there. So, where is the actual process residing? The actual process, the whole address space is typically residing in some area of secondary memory, let us say disk. Now, traditionally in the older versions of the operating system, there was a special area of the disk. If you say that this is my disk, there was one part of the disk which was designated as the swap area. So, this process, for whichever process is running, they used to be stored in the swap area, and whenever some part of the process is required, it will be brought by the operating system from the swap area. But the modern versions of the operating system, what they do not store it in a separate swap area. Wherever in the file system the executable program is there, from there itself they can bring that relevant part. Okay? So, there is a clear improvement, you do not have to copy that into swap area and then bring it from there. So, there are many versions of the operating system where either of these two are used. Okay? Fine. Now, this concept where we are partially loading the program in memory, this is called virtual memory, and this is the topic of our discussion in this present module. So, some of the advantages I have already mentioned. Let us clearly enumerate what are the advantages we gain if we have this kind of virtual memory. First thing is that since we do not have to load the entire process in memory, the size of a process can exceed the size of the physical memory. Suppose I have a 1 gigabyte physical memory, I can have a process whose size is 2 gigabytes, because only part of the process will be loaded at a time. And secondly, I have already mentioned this, each process will occupy less memory because we are not loading the whole thing. Because it occupies less memory, you can accommodate more number of processes. So, in multiprogramming on time sharing, you can load more number of processes in memory which are in the active state. So, you can have greater number of processes running at the same time. Because there are greater number of processes running, clearly you can have improved CPU utilization and throughput, because CPU will never be waiting, always there will be some process in memory which are in the ready state, because there are many processes now. So, this can lead to an improvement in CPU utilization as well as net throughput. And secondly, because you are not loading the whole process in memory, you are having less read operations from the disk. As you know, secondary memory access is slow, whereas main memory access time is of the order of 50 to 100 nanoseconds typically, disk access time is of the order of milliseconds. So, because we are loading less amount of information into memory from disk, that transfer time is also less disk transfer is required. This is the last advantage listed here. Okay? Fine. So, we mentioned earlier that there are two things, one is logical address space, which is defined with respect to the address that the CPU generates. CPU during execution of a program generates some address which is termed as a logical address. If the logical address is, let us say it is 32 bits, then my logical address space will be maximum 2 to the power 32. Okay? Similarly, when you have your memory, this is your physical memory, main memory. So, when you access the memory finally, you access it by its physical address. This is called the physical address. So, in virtual memory, we are totally isolating logical address from the physical address, because we are not loading the entire logical address into memory at the time. So, you can say that in virtual memory, we can achieve complete separation. In normal paging, there was a separation, but there was a restriction that the entire logical address space must be residing in the main memory, but here we are also relaxing that restriction. So, there is a complete separation, you can say, between the logical and the physical address spaces. So, as I said, only the relevant parts of a process need to be loaded in main memory when we execute. Now, typically, well, let me say clearly, this is not in general true, there can be exceptions, there can be other way around also. Typically, logical address space is greater than the physical address space. What do you mean by that? Let us say in some typical computer system, if you see, you will find that the CPU generates an address which is either a 48-bit address or a 64-bit address. Let us say the CPU generates a 48-bit address, which will be the logical address. So, my logical address space will be how much? 2 to the power 48, so many bytes. But my main memory, when you are accessing the main memory, it may be addressed by less number of address line, let us say 32 bits. So, if you have 32-bit physical address, then your physical address space will be 2 to the power 32. So, obviously 2 to the power 48 is much greater than 2 to the power 32. So, a large process can possibly be accommodated in a physical memory which is of a much smaller size. Okay. This is the essential idea behind virtual memory, and this logical address space that we are saying, that logical address space is sometimes also referred to as virtual address space, because it is virtual. So, that exactly does not mean that the same thing is there in the physical memory, parts of it are loaded. Okay. And as I mentioned earlier also, logical address space or the virtual address space for a process, if you look at it conceptually it will consist of a number of bytes or words. It starts typically starting from address 0 up to some maximum. So, when it is loaded into physical memory, there will be a logical to physical address translation. We saw how using page table we can do that. That is the main task of the memory management unit, to map logical addresses to physical addresses. Okay. This is essential. See, whatever I said here is very similar to what we did in paging, but we have to do something more to make sure that we can have a scenario where only parts of a process can be loaded in memory at a given time. Okay. Fine. Now, the question is, conceptually it is fine, virtual memory. How do we implement virtual memory? See, broadly there are two approaches as is shown in this slide. One is called demand paging, other is called demand segmentation. Now, in demand paging, as the name implies, so the word paging is there. So, this method is based on the paging memory management scheme which we already discussed, but there is another word we have added, demand. See, earlier what we said, that all pages of a process needs to be loaded into physical memory, but now we are saying no, we will be loading the pages on demand. Whenever those pages are required, only then we will be loading the pages in memory, otherwise we will not load. So, less memory space will be required overall. And demand segmentation is something similar, where instead of pages we talk about segments. Now, in a program, instead of pages you can think it as a number of segments. and segments can be of different sizes. Let us say one can be your main function, one can be some library function, let us say, one can be, let us say, your stack, one can be your data area. These are logical parts of your program which you can understand, but pages are just equal size chunks. Segment means the logical groups or entities that constitutes a program, and demand segmentation is something similar. You load the segments on demand. So, whenever some library function is called, only load that library function at that time. Okay. So, essentially different parts of a process are divided into something called segments which are unequal in sizes, and the segments are typically considered as a logical unit of the program. As I have shown here, there can be the main program, there can be library functions, stack, data area, and so on. Now, you can see that we can also combine the concepts of demand paging and demand segmentation. Let us say we can have demand segmentation where you load the segments on demand, but every segment, let us say the main segment, we divide into pages. So, when you load the main function into physical memory, we use paging, we divide them into pages and load the pages in memory. So, process is divided into segments, this is the first thing, and each segment is further divided into pages. So, this is a combination of paging and segmentation, this also we can have. Now, many of the practical computer systems, they use this combined version also, some of them use just paging. Okay. Fine. Now, pictorially let us see conceptually how virtual memory works. First thing on the right, you see the backing store, which is nothing but the secondary memory. This is the, just assume that we are using paging. So, the pages of a process will be stored in secondary memory. Now, I said that there are two ways we can store it, either you can store it in a separate part in the secondary memory called swap area, or you can store it as part of the same file system where the executables are stored. From the executable itself, the pages are extracted. So, whatever it is, conceptually I am showing it like this. These are the different pages of a process. So, all the pages of the process are initially present in the secondary memory. Okay. On the other side, you have the virtual memory. This is a process. The process consists of a number of pages, let us say page 0, page 1, page 2 up to some maximum. Okay. Now, these pages are mapped into main memory. Here you have the physical memory. Then you have this memory map, which is nothing but what you have seen as the page table. Page table creates a correspondence between the logical address and the physical address, the pages and the page frames. Which page is residing in which page frame? For example, page 0 may be residing here, let us say. This is page 0, this can be page 1 and so on. Now, in virtual memory, the idea is that not all the pages are loaded in physical memory. You first consult the page table. So, there will be some information kept in page table whether the page you are trying to refer is presently in memory or not. If it is in memory, fine, just like the previous paging method, you go to memory and access it. But if it is not, then you will have to load that page from secondary memory into physical memory. After loading, naturally you will also have to update the page table to indicate that now the page is loaded, now the page is available in memory. And sometimes it may happen when you are trying to bring a page in memory, you may see that my physical memory is already full. I do not have any free page frame where you can bring it. So, under that scenario what you have to do, you will have to remove one of the existing pages from memory before you bring the new one in. So, this is the arrow, and these two processes are sometimes called swap out. You are bringing a page out from the memory, or swap in. The point to note is that when you are swapping out, if you see that the page was not modified while it is in memory, you can simply throw it away. But if you find that the page was modified, some changes were there, some write operations were there, then when you are doing swap out, this page has to be written back into the corresponding page in the secondary memory, because otherwise that change information will be lost, right. So, conceptually this is how virtual memory works. Okay. Now, talking of the virtual address space, I said virtual address space is nothing but the conceptual view of a process starting from address 0. Now, we saw earlier that in typical operating system, the address space comprises of different regions, like as is shown here, text or code region, data region, heap region, and finally the stack region. Now, we said in Unix or Linux or even other operating systems, typically this stack and heap, they grow in different directions. When you push some data in the stack, typically this is the lowest memory address, this is the highest memory address. So, when you push something in the stack will grow from the higher to the lower memory addresses like this. And heap is a place where you dynamically allocate memory. So, when you are dynamically allocating memory, for example, in C you can use malloc or calloc to dynamically allocate memory. So, then it is created in the heap area, and heap area will be growing in the other direction from the lower to the higher memory address. Okay. So, now you see, if you think of a process, this is the picture of the whole process address space. This is the entire region, but the point to note is that there is a part in the middle which is kept vacant for expansion of the stack or the heap. At any given point in time, if this denotes the snapshot of the process, that middle part does not contain any valid data. So, you can say that this part is valid, this part is valid, but the middle part is invalid. So, you will also keep some information that when you are accessing memory, whether some addresses within the logical address space is valid or invalid. Invalid means there is nothing, no meaningful data is stored there. Okay? Understood? Fine. So, this is what is explained here, that the vacant region between heap and the stack, this we refer to as the whole region. This is actually a free space where nothing is there presently. So, no physical memory needs to be allocated to this region, because there is no meaningful data presently stored there. Okay. So, this, as I said, that this so called whole region is kept either for dynamic memory allocation for the heap to grow, or for recursion or function calling where stack can grow. Okay. Similarly, when you are having some system libraries loaded in memory like math library, standard input, many libraries are there. So, when some library is loaded in memory, it is possible that two or more processes may be sharing the same libraries. So, instead of loading the libraries multiple times in memory, you can have them stored in one place in the physical memory, but from the different logical address space you can map to the same addresses, same pages, same page frames. Okay? This is possible. Okay. Now, let us look at the first method of implementing virtual memory, demand paging. So, we shall be discussing demand paging in more detail. Demand segmentation we shall mention very briefly. Demand paging, as I said, this is a memory management scheme which is essentially based on the paged memory management, basic paging. So, what we do in paging? We repeat it once more. The virtual or the logical address space of a program, suppose this is my virtual address space, we divide it up into equal size pieces called pages, equal size pieces or chunks which are called pages. Similarly, the physical memory is also divided into some segments of the same size, some blocks of the same size. These are called page frames or blocks. A page may be loaded in page frame as we have seen in paging earlier. But with respect to paging, what is different in demand paging? Let us understand that. What is actually different? This is important to know. First thing is that is the spirit of virtual memory, only a subset of the pages are loaded. We do not load all the pages of the logical address space into physical memory. And how do you keep track of that? We must store the relevant information in the page table. Page table must keep track of that. So, we shall see later. We add some additional fields in the page table. Earlier we saw that the page table contains only the frame number, so that the page number of a logical address can be replaced by the frame number, you get the physical address. But now we will see some additional information is also kept, whether a page is valid or invalid. If it is valid, you can access. If it is invalid, you will have to load it from memory, right. Now, when a page is referenced, suppose during execution of a process, the CPU accesses a memory location that is mapped to some page. So, there are three things which are possible. First is that the page is present in memory as indicated by the page table, that there is a page table entry, it is marked as valid. So, you can get the frame number for there and you can directly access that page, no problem, exactly same as in normal paging. But if the page is not in memory, you find that the corresponding page table entry is marked as invalid. Now, there are two conditions possible that the operating system has to decide. Once the page table entry is marked as invalid, a page fault exception will be generated. It is called page fault. It is a exception or an interrupt that will be generated automatically. Page fault means it is an exception which arises when the requested page is not currently in memory. If that valid invalid bit is marked as invalid, a page fault exception will take place. Now, the operating system will decide, OS will decide whether it is actually a page fault exception, that means the requested page is not in memory. If so, it will be loading the page from secondary memory. But it is also possible, as I said, that in the process address space there can be some parts where no data are stored, those are invalid areas. So, operating system can also check whether the requested page falls within one of those invalid regions. So, if it tries to access an invalid page, then some error message has to be flagged and possibly the process will be stopped, execution will be aborted. Okay? Fine. Now, as I said, the basic mechanism behind executing a program, what you can do? Like classical paging, we can bring all the pages in memory before execution starts. but we said in virtual memory or demand paging we are not doing that. We are loading only a part of the program at a given time. Whenever a new page is required, we will be loading it on demand. So, the idea here is that we load a page in memory when it is needed, that means on demand. This is the basic idea. Because we are doing it, then the parts of the process which are not actually needed during execution need not be loaded. So, it eliminates all unnecessary disk input output operation. You do not have to load them from the disk. As I said, because the disk is much slower as compared to memory, this will lead to faster response. And because we are occupying less memory per process, you can have better memory utilization, you can accommodate more number of processes, that means more number of users can run their programs. So, basically this is not anything drastically different from paging, we are just enhancing the capability. Paged memory management was there, we are enhancing the capability by including one new feature which is on demand page loading. So, when you load a page, it can also lead to swapping. Swapping means exchange, interchange. As I said, when you are accessing a page which is not in memory, you will have to load it from the disk. If you find that currently your main memory is already full, there is no free page frame, you will have to remove one of the pages from memory, make a free space and then load the requested page. Swapping means you are swapping out something, you are swapping in something else. One page goes out, another page comes in, that is swapping. Okay. Fine. So, pictorially this is just a depiction. Let us say there are two programs, program A and program B. Due to some reason, if the entire program gets swapped out, you see this is your secondary store, or you can say this is my swap area. Here the entire address space of the program A, program B both are stored. Let us say this program A will consist of 4 pages. These are stored in page numbers 4, 5, 6 and 7 in the disk. So, when you are swapping it out, the pages that are updated, they will have to return back into 4, 5, 6, 7, but not all the pages, only the pages which you have changed or modified while they are in memory. Similarly, when you are loading some new pages, for example, program B, you are loading 3 pages, suppose they are loaded here, they are present here, here and here, they will get loaded into main memory. Okay? This is how it works basically. Now, as I said earlier, let me repeat. So, when this on demand page loading business comes into the picture, it introduces an additional challenge. This already I mentioned, just we are repeating. So, when you are bringing in a page, that can result in some page being swapped out. Why? I said it can so happen that the memory is already full and some process is requesting a new page. So, the new page has to be loaded, we do not have any space in memory. So, one of the pages have to be swapped out. Now, in terms of terminology, the unfortunate page that you are throwing out, that is referred to as the victim page. So, you are selecting a victim page from main memory, you are throwing it out, swapped out, and you are bringing in the new page. Okay. And this is of course Second point is the essential idea behind demand paging. Pages can be swapped in to the memory from the secondary storage, because a process can access a page which is not currently in memory. If it is not in memory, the page has to be loaded, only then the process can resume its execution. The process has to wait while the page is being loaded. Okay. Now, as I said, when you are swapping out a page, you have to select which of the many pages in memory have to be swapped out, that is the victim page. So, now there is it may so happen that the page you are removing, that the victim page that you are selecting, very soon you will be requiring that same page again. So, you will have to again load it back. So, it is desirable to select the victim in such a way that you will not be requiring that page for at least some period of time. This we shall see later how we can do that, how we can decide on that. So, decision on which victim page to be removed, this is a new decision that needs to be taken by the operating system, and there are many so called page replacement algorithms that we shall be discussing. And the basic idea or intuition behind this page replacement algorithm is, this is mentioned here, that do not remove a page if it is likely to be used again in the near future. But you see, the operating system is not an astrologer, the OS cannot see the future, but somehow it can predict what might happen in the future. This is what we shall see later. You try to select a victim such that it is least likely to be used in the near future. Okay. So, how to predict the future, this we shall be discussing later. Now, we said, we already mentioned that when pages are there, some of the pages of a process are loaded in memory, the page table has to store some additional information, whether a page is currently in memory or not. So, this is done using something called a valid bit, because what we need, this is a requirement of demand paging. When a process is running, when the CPU is generating an address, you are accessing a page, you need to know that the page you are accessing is valid or invalid. Basically, we want to know whether the page you are accessing is currently loaded in memory or not. If it is currently loaded in memory, we can go ahead and access it. But if it is not loaded in memory, then we will have to wait for the operating system to swap that page in, then only it can restart its execution. So, it is a decision whether the page is currently loaded in memory or not. So, this is typically done by adding one additional field. For example, you know how this page table was there. Earlier page table contained only one field, the frame number, but now what we are saying that we have this frame number, one field, there is another field we are adding, valid or invalid. Valid invalid is basically a single bit, 0 can indicate valid, 1 can indicate invalid, or the reverse. A single bit is sufficient. So, we have to add one bit to every entry in the page table. This is referred to as the valid invalid bit. So, this bit indicates whether the corresponding page table entry, suppose one entry in the page table is there, this entry, whether that entry is valid or invalid. If it is marked as invalid, which means the page is currently not there in memory. So, it indicates whether the page is valid or invalid. As I said, here I am denoting it as V and I, but actually in actual implementation V can indicate 0 possibly and I can indicate 1 or the reverse. So, initially before a process starts execution, all the bits are invalid because none of the pages are loaded. Now, as the pages get loaded one by one, some of the bits change from I to V, they become valid. The value of V indicates that the page is currently in memory, while invalid I indicates it is not in memory. Okay. Now, another thing we already mentioned, that when the memory management unit is carrying out this address translation, logical to physical address translation, so whenever the page requested is not in memory, so how do you know that? You check that the page table entry is I, that means it is not in memory. That will result in a page fault exception. Exception is like an interrupt which is generated from internal to the processor while executing an instruction, that interrupt is generated. When you run a instruction, execute an instruction, you access the page table, you see that the bit is I, so the page fault exception will be automatically generated. Okay. Whenever the corresponding entry contains I, this page fault will be generated, and now the operating system has to be given control to load the requested page into memory. Okay. Fine. Now, there is one very important point. Let us digress a little bit. See, in computer organization, I hope many of you have studied interrupts. I am talking of hardware interrupts. Every processor has an interrupt pin through which whenever some external device sends an interrupt, the processor acknowledges the interrupt, control jumps to some interrupt handler or interrupt service routine, some routine is executed and control returns back to the program which was executing. Now, there normally what is done is that suppose an instruction was executing, it was in the middle. If an interrupt comes, the instruction finishes execution, only after that interrupt is acknowledged. Okay. So, the hardware allows the instruction execution to complete, only then interrupt processing will start. But for page fault, you think, can the instruction execution be completed? Because the process was trying to execute an instruction which is referring to a memory location which is in some other page, that page is not in memory. So, how can that instruction finish execution? The data it is trying to access is not there in memory. So, it cannot finish execution. So, page fault exception is entirely of a different type. See, for a normal interrupt, when you return back from the interrupt handler, you restart from the next instruction following the instruction which was executing. But now, the instruction which was executing, that caused the page fault interrupt and that instruction could not complete. You have to come back and restart that instruction, not the next instruction. Okay. So, that is mentioned here. Page fault exception, first thing, is not like any other normal interrupt. As I had explained, the instruction that was executing, when the exception occurred, why the exception occurred? Because there was a page fault. Why page fault occurred? Because you are trying to access a memory location which is not in memory. So, naturally the instruction cannot be completed because the data it requires is currently not in memory. So, after returning from the interrupt handler or interrupt service routine, the instruction has to be restarted. This is very important to remember. Let us take one small example. Let us take a hypothetical computer architecture instruction. Load R5, 2500. Let us say this instruction means that you load register R5 with the value which is stored in memory location 2500. So, when this instruction is executing, what will the CPU do? It will first access memory location 2500, read the data from there and then copy that data into register R5, right. But it may so happen, let us say if you think of the logical address space, these are the pages, let us say. Now, this load instruction may be part of one page, this load instruction was here, and this 2500, that may be part of another page, this may be here. And possibly at the present this is valid, of course, this is valid because it is executing, and the second page was invalid, not in memory. So, if it is invalid, whenever this load instruction is trying to execute, it will generate a page fault interrupt, page fault exception, because memory location 2500 belongs to another page which is currently marked as invalid in the page table. Okay. This can happen, right? Fine. Now, let us look into one example at the end where this kind of a scenario can take place. Let us consider that we have some process running here, let us say process Pi. This process Pi consists of a number of pages, let us say A, B, C, D, E, F, G, H. There are 8 pages. And let us say small example, we have a physical memory, there are 0 to 15, 16 page frames, there are 16 page frames. And as I said, all these 8 pages must initially be stored somewhere in the disk, in the secondary memory. Let us assume in the backing store, so the 8 pages are here, A, B, C, D, E, F, G, H, they are somewhere. And whatever we are showing here is a snapshot of the execution at any particular point in time. Let us assume this is my scenario. This is how this scenario looks like. Only pages A, C and F are loaded in memory. The other 5 pages are currently not loaded. Okay. You see the page table, you can understand how this information is maintained there. Since the process contains 8 pages, there will be 8 entries in the page table. The entries are indexed by the page number. And the first entry in the page table, as I said, page table will contain 2 entries. One is the frame number and the other will be the valid invalid bit. So, you see only 3 pages have valid page, 3 entries have valid page numbers corresponding to the pages which are currently loaded. Page number 0, which is A, page number 2, which is C, and page number 5, which is F. So, A, C, F are the 3 pages which are loaded. So, you see the corresponding entries are marked as valid V, V, V. All the other 5 pages which are currently not in memory, the entries are marked as invalid. So, you can see there will be some kind of a hardware mechanism where these valid invalid bits can be stored in a very fast register. Whenever a page access is done, first the hardware itself can check whether the corresponding bit is valid or invalid. If it is invalid, automatically interrupt is generated, and if it is valid, it will be allowing it to access the main memory, right. So, and one problem that was there with normal paging still remains here, that when you want to access main memory, you are actually accessing main memory twice. First you are accessing the page table, from there you are getting the frame number. So, I am repeating what you do in this translation. In the logical address, we have the page number and the offset. In the physical address, you have the frame number and the address and the and the offset. So, the offset is simply copied, but P to F, this mapping is done using the page table. The field P is replaced by the corresponding value in the page table, that is F, the frame number, and that gives you the physical address, and with the physical address you can access the main memory, right. So, this is how generally this valid invalid bit works. And another thing I told you, another utility of valid invalid bit is to mark which parts of the process address space is currently not used, that can also be marked as invalid. So, when the exception comes, operating system will decide whether it is simply a page fault, that the page is in the disk, you have to bring it, or that page is non-existing in the process address space, that the OS will decide. Okay. So, with this we come to the end of this first lecture of this module, where we firstly we tried to motivate ourselves why we need this concept of virtual memory, where we want to load only parts of the logical address space in physical memory during the execution of a process. And then we started the discussion on one of the most commonly used virtual memory management scheme, namely demand paging. In the next lecture we shall be continuing with the discussion. We shall be looking at many other aspects of virtual memory, page replacement schemes and so on. So, we shall be discussing them in the next few lectures. Thank you.